everyone, I'm Gail, and now I am about to share to you my knowledge about one of the topics in basic calculus. I am going to teach you about continuity and its consequences. We are going to determine whether function f is continuous at point A, or if it is discontinuous, is it essential or removable. So what is continuity? For a function of f defined in an open interval containing x is equals to a, we say that f is continuous at a when the limit of the function of x, where x is approaching to a, is equals to the function of a. So the values of these two must be equal to each other. So if these two aren't equal, otherwise f is said to be discontinuous at x is equals to a. So if these two values are unequal, then we would have a discontinuity. So this is just a broad definition of continuity. Now let us go and narrow the definition. So narrowing the definition, we are given with three conditions. First one, the value of the f of a must exist. It must be defined. There shall be no indeterminate or undefined value of the f of a. Condition number 2 states the same also for the limit of the function of x where x is approaching to a, that the value of this must exist. So the third condition, the existing limits of the f of a and the limit of the function of x where x is approaching to a must be equal to each other or with each other. So now, if one of these conditions aren't satisfied, we would have a discontinuity. So discontinuity is varied into two. First one is that the essential discontinuity. So when we have an essential discontinuity, it wouldn't satisfy the condition number 2. So in the second step of discontinuity, the removable discontinuity, it states that if f satisfies condition 1 and 2 but fails to satisfy condition 3. So in order to satisfy condition 3, we could manipulate or redefine this type of discontinuity for it to finally be continuous at point A. So now I'm going to present to you three examples. So example number 1. We are given with the function of x is equals to x cubed plus 2x plus 1, where point A is equals to 2. So first condition, we're going to find the f of a. So we are going to use this equation, x cubed plus 2x minus 1. And then, since x is equals to a, then we are going to substitute the value of a into here, into the x. So we are going to have 2 cubed plus 2 times 2 minus 1. And according to the PEMDAS rule, we should solve first the exponent, then the multiplication, and then the addition before we subtract. So now, 2 to the power of 3, we have 8. 2 times 2, we have 4 minus 1. We're going to add 8 and 4 together. We are going to have 12, then minus 1. We're going to subtract 1 to 12, so we would have 11. So the value of the function of a is 11. 11 is no indeterminate or undefined number. Therefore, this one exists. So now, as we have our f of a, we will now solve for the condition number 2. So, the limit of the function of x, where x is approaching to 2. We would still use this equation, x cubed plus 2x minus 1. And then, since x is approaching to 2, we would substitute 2. So we would have 2 cubed plus 2 times 2 minus 1. According again to the PEMDAS rule, we will solve first 2 to the power of 3, 8, and then multiply 2 times 2, we have 4. And then add 8 and 4 together, we will come up to 12, and then minus 1, we would have 11. So, the value of the limit of the function of x, where x is approaching to a, or the R2, is 11. 11 again is an existing number. So, since f of a and the limit of f of x, where x is approaching to a, exists, we can now proceed to condition number 3. So, condition number 3, these two values, f of a and the limit of the function of x, where x is approaching to a, must be equal to each other. So, since 11 is equals to 11, then this function is continuous at point A. And now, we will proceed to example number 2. So example number 2. We are given with a piecewise function. Function of x is equals to x squared with the given condition that x is equals to 5. And x plus 7 over x squared minus 5 with the condition x that is unequal to 5. And with the point A is equals to 5. So, first condition, we will solve for the f of A. So, why will we use x squared? So, we will use x squared because it satisfies the condition that x is equals to 5. You see, A is equals to 5, and we know that x is equals to A, right? So, this one satisfies the condition that x is equals to 5, okay? Because of this one. That's why we will use x squared. So now, given with the x squared, we will substitute 0.5. This one is equals to 5, okay? So, yeah, substituting 5, we will be given 5 squared. So, 5 to the power of 2, we would have 25. So, the value of f of A is 25. And 25 is an existing number. It is not indeterminate nor undefined. Proceed to condition number 2. So, we will solve for the limit of the f of x where x is approaching to our A, that is 5. So, why will we use this equation? We will use this equation because of the given condition that it is limit x is only approaching to 5, not really equal to 5. So, like this, x isn't equal to 5. It is really not equal to 5. So, that's why we will use this to solve for our limit. So, given x plus 7 over x squared minus 25, we will substitute 5. Since x is approaching to 5, right? So, we have 5 plus 7 over 5 squared minus 25. According to the PEMDAS rule, we will solve first for the exponent. So, 5 to the power of 2, we are given with 25. And then, let's add, and then subtract according to PEMDAS rule. 5 plus 7, we have 12 over 25 minus 25, 0. So, 12 over 0 is an indeterminate number. And therefore, since the value of the limit of the function of x where x is approaching to A is an indeterminate number, we are now having an essential discontinuity. The function is discontinuous at point. The piecewise function, is discontinuous at point 5. Now, let's proceed to the last and third example. Example number 3. Again, we are given with a piecewise function. F of x is equals to 1 with the condition x is equals to 1. And 8 over x squared plus 3 with the condition x is equal to 1. And point A is equals to 1. So, first condition, f of A, since x is equals to A and A is equals to 1, x must also be equals to 1. So, 1, the constant 1 satisfies this condition. That's why we will use 1. And since 1 is constant, we are then given with, of course, 1. The value of f of A is equals to 1. And 1 is an existing number. It exists. The value of f of A exists. Now, condition number 2. So, condition number 2, the limit of the function of x, where x is approaching to 1, we're going to use this equation since, as I said earlier, it is approaching not really equal to 1, and the condition of this equation is not equal to 1, so we will use this one. So, yeah, 8 over x squared plus 3. So, since x is approaching to 1, we will substitute 1. We would have 8 over y squared plus 3. Solving for the exponent first, 1 to the power of 2, we have 1. And then adding before dividing, 1 plus 3, we have 4. And then let us now divide this 2. 8 divided by 4, we have 2. So since 2 is not an undefined number nor an indeterminate, it is existing. So the limit of the function of x, where x is approaching to A, exists. Since we have the value of the f of a and the limit of the function of x where x is reporting to a, we will now proceed to condition number 3. So, the value of f of a must be equal to the limit of the function of x where x is reporting to a. But 1 is unequal to 2. So, since these two values are unequal and it dissatisfies condition number 3, but satisfies condition 1 and 2, we are now having a removable discontinuity. But not to worry. This is not done yet because in removable discontinuity, we can manipulate it. And now, we will make the function of 1 be function of x with the condition x is equals to 1. So solving for the f of a, it is f of x that satisfies the condition. So we will use the constant 2. Since 2 is constant, the f of a will still remain as 2. And since 2 is a real number, it is existing. So the value of the f of a exists. Let's proceed to condition number 2. So we all know in this computation that the limit of the function of x where the x is approaching to 1 or to a is equals to 2. And 2 is an existing number. Then, after having these values of f of a and the limit of the function of x where x is approaching to a, let us now proceed to the condition number 3. So, condition number 3, f of a must be equal to the limit of f of x where x is approaching to a. And the values of these two are equal to each other. So, finally, the piecewise function is continuous at point 1. Now, after this, let us sum it up all together. What is continuity? Continuity is when function f is continuous at point a, if and only if the value of f of a exists, so as the value of the limit of f of x, where x is reporting to a, and if these two existing values are equal to each other. And if one of these conditions is dissatisfied, then we would have a discontinuity. So 2 types of discontinuity. We have essential, when condition 2 was not satisfied, and removable, if it satisfies condition 1 and 2 but fails to prove condition number 3 to be true. But don't you worry, because this type of discontinuity can be manipulated so that finally the function f would be continuous at point A. And that would end this lesson. Thank you for listening, and I hope you learned something. Bye-bye!